Thank you. So what I want to tell you about is extended geometry, what it is. It's a unified framework for what David told you about earlier. Double geometry, exceptional geometry, etc. Turns out you can do everything at once with a unified formalism. It's not very complicated. In fact, it's sort of easier to do it all at once. You get the general structure. Although I must declare from the beginning that what I'm doing is not strictly speaking M theory or supergravity or anything. I will only do bosonic fields. Maybe if I feel like it later, I will tell you something about fermions, but maybe not. I will only deal with what from the a dimensionally reduced or compactified theory, from that perspective would be the internal space. That means what from the external remaining space-time would be the scalar sector. Gravity on the internal space dressed up with other fields. Because in the general framework, I don't know what is an external space, what is the appropriate. If I'm in the exceptional series, I know that it comes from a duality. I know the dimension of the external space, but in general, I want to keep that open, so I don't specify that. So next point on the list of what I'm not doing, I will not at this point be able to do anything globally, meaning patching things together to a global gerb, whatever. But I would be happy for any suggestion on how to do that. I don't know what a finite transformation is, essentially. Okay. But so I've ticked the most off the list, but there are a few things that remains to be actually done. So I will start by writing down the same gauge transformations that David gave you earlier. And the gauge transformations are generated by what we may call a generalized Lie derivative. I use the index m. I will tell you what it is in a little while. Some representation of something. And it I will write it in two different ways. This is the way David wrote it earlier. It's not the actual Lie derivative, but it differs from being that Lie derivative by a term like this. This is identical to what David showed you. This is an invariant tensor in some sense, which I will also come to in a minute. But I would also like it to write it on another form, which I think is maybe more suggestive, namely, hi David, I was just talking about you. The Lie derivative is anti-symmetric in the psi and the v, and I want to split off the second term in the Lie derivative in order to display the similarity of this generalized Lie derivative to the ordinary one, namely split it into a transport part and some transformation part. Like this. Where, of course, there is an extremely simple relation between y and z. y is z plus delta delta, I mean the remaining term in the L. Now, what does this mean? What are these letters? This is an index that labels a representation of Lie algebra, G. Which is a Kac-Moody algebra. It's not getting dramatic yet, but it may if you, later. You can turn it on again in 20 minutes, say. And so, what kind of representation does V sit in? For convenience, we say that it's a lowest weight representation. We could take highest weights. It's just a matter of conventions. So it's the lowest weight representation where lambda is dominant and integral highest weight. So this is just my private notation for lowest weight. So what happens if I do this? Well, clearly so I could have said that this is OD, D, or I could have said it's one of the algebras in the exceptional series, and you would be back to David's talk. And then the appropriate, in those cases, finite dimensional, highest and lowest weight representations of that algebra. And of course, Y, or equivalently Z, is an invariant tensor under the action of this algebra. Otherwise, it's not meaningful. But there is something more you can ask, namely that this should be a transformation that actually sits in G. So you rotate, it's not really meaningful unless you rotate V by something which lies in G itself. This means that this pair of indices should be G valued, and actually I should add maybe also some scaling, because there might be some weight involved. There is clearly some weight involved already in gravity, so let's allow for that. And also these indices. So when we invented those tensors, I don't know, 6 years ago or something, 5 or 6 years ago, it was a bad idea to put the indices in this order. So I mean, I considered a couple of years ago switching, but that would already be more confusing. So they were kept in this order. It's more natural would be more natural to have them in the other order. If you think about what can you write down that takes these values? It's not much. I mean, you don't have much choice. There's one invariant tensor that is G valued in a pair of indices, and that's let me write it on index-free notation. So I think of this as acting on some pair of indices. One is this, where I contract with the killing metric. So already this is a restriction. I assume that there is a killing metric, non-degenerate Cartan matrix. But if it's degenerate, I just fill in some extra generators, like you do for the affine algebra, for example. You can add in L0. So, I mean, this there's a well-defined procedure. So it's not really a restriction, but in the end, you end up with something which is non-degenerate. So that's one. Another term, of course, is the unit thing, which does scaling. And since I had the indices in wrong order, I should not write sigma equals that, so zeta equals that, but sigma, where this is the permutation, switches to indices. So, and then I have this. So I have two constants to determine. Well, and then I have to check the algebra, of course, that this is meaningful. Turns out I want a minus here. It turns out I want this number, where this is the length square of the lowest weight. That's it. You can check that this reproduces the ODD stuff that David told you, and that it actually reproduces the exceptional series that David didn't tell you in detail, but told you on sort of this level. You get the right things, the known things. And this you can do for any Kac-Moody algebra this far. How do we know that these numbers are supposed to be there? Well, we know it because we check the algebra. We check that commutator gives that, plus maybe some extra stuff which I will come back to. T alpha are the standard generators. This is an adjoint index. This is just multiplying delta delta. So I mean, it's the identity. I could write times identity tensor identity, but I didn't because. That would be that this number would multiply delta NP delta MQ. Z is something that maps the tensor product of two such things on itself. Maps V tensor. Okay. To upper to lower. So these are generators, or more precisely, representation matrices in this representation. Yeah. Absolutely. Half a minute. This is just the anti-symmetrized Lie derivative again. Sometimes this works, sometimes you get something else. Let me give it a name already now. Anti-symmetrized. So this would be what you may call a Dorfman thing, and this is what you may call a Courant thing, but it's for any. So, of course, anything, if I allow that to be anything, it will always be satisfied, but I will not allow that to be anything. it will be restricted. It would be something very, very special, which I will tell you later, roughly. But this, of course, only happens. So for double field theory, this is absent. For exceptional field theory, up to E7, where David drew his line, it's also absent. For E8, it starts popping up. Essentially, if you go what corresponds to reduction to 3 dimensions and lower, you can't get rid of these. They have a role to play. For E8, for example, what does it do? It's a transformation that actually saves you from the dual graviton. It can be used to transform away the dual graviton. It has to do with mixed tensor fields. But of course, this is modulo section constraint. And the section constraint always reads strong. So I let this thing act on 2 derivatives. The 2 derivatives act on each on anything. Without that, without the strong constraint, I don't know what the gauge, this does not happen simply. So I don't know how to relax this. Huh? Y. It's the Y tensor. It's always the Y tensor. Yes. This constraint we can understand actually in a very algebraic, geometric way, because think of these as momenta. Any momentum belongs to a minimal orbit. That's sort of the strongest constraint you can possibly put on something. Minimal orbit means minimal orbit of this representation, of R. The conjugate representation under the group, the Kac-Moody, the exponentiation of G. There is a I put quotation marks here. It tells you where these numbers come from. If you have something in a minimal orbit, you act with what looks like the quadratic Casimir operator. You have to be a bit careful if it's infinite dimensional, but there is a well-defined procedure for normal ordering, etc. And the value is always this. And that's essentially what this will tell you. I don't spell out the details. Now this would be the weak section constraint, though. Defines a cone. It's not a linear space. The strong constraint states, or the result of the strong constraint is that momenta lie in a maximal linear subspace of this minimal orbit, where all momenta mutually sort of satisfy a constraint roughly like this. So it's a linear subspace of the minimal orbit. So that's a nice picture. Okay. So I could give you I think I will skip the explicit form of the sigma because it's not very enlightening, but it's just using Lie algebra and representation theory, we could give a list of situations where these transformations, which we call ancillary transformations, when they are absent. If auxiliary hadn't been taken, we would have called them that, but now they are ancillary. They vanish exactly when G is finite dimensional and lambda is a fundamental weight with that is dual to a simple root with Coxeter label 1. This is equivalent to the scalar product between lambda and the highest root is 1. That's the full statement. This is sort of unnecessary. If this is not true, there is no theta. And so there is a finite number of cases, which I maybe will not list, including double field theory, exceptional field theory, etc. And also some funny cases, but never mind. Sorry? Theta is the highest root, which only exists if it's finite dimensional. Sorry? The highest root, the highest of the roots. There is always a unique highest root for a finite dimensional simple Lie algebra. Sorry? Some of all simple roots with coefficients which are the Coxeter labels of the respective roots. Okay. Good. So, as David mentioned, so in all other cases, this will be present. So I will leave that discussion for a little while, and I will come back to it. As David mentioned, so now I switch from this R minus lambda, which is the actual representation, and call this R1. This is the coordinate representation. It's upstairs indices. There is a reducibility. Some other representation. I call it R2. For the double field theory, this is a singlet. It's the same thing as the reducibility of, because this contains the gauge transformations for the B field, which has a singlet reducibility, and that's all there is also in the doubled case. So you can map from here to there with something which involves a derivative. When I talk about fields taking values in these things, they also, of course, are functions of coordinates living in these. Okay. In the exceptional cases, as David mentioned, this will go on. There is a secondary reducibility, which you would expect if you have a 3 form, and then you would expect it to stop there. But you can also have 5 forms, so it actually goes on. But you might expect it to stop somewhere, because the reducibilities of the 2 form and 5 forms are finite. However, this does not happen. Reducibility is sort of depends on how much covariance you want. I want, in those cases, the full exceptional algebras, and in order to get representations of those, I have to fill in with new stuff that starts new sequence of forms that start somewhere and stop somewhere else. And these will also carry some other representations, and this will cause funny things to happen. Anyway, this goes on typically forever. Not in every case, not in double field theory, but in exceptional field theory, for example, and certainly in the generic case. I'm sure it's controlled. So when I calculate, if I would... Depends on how you see it. Let me give you one example. No, nah. E5 is spin 5-5. There, this is E5 from the wrong, and here is lambda sits here. Then this is 16, this is 10, this is 16 bar, this is 45, and then I don't remember the details. So when I calculate the actual number of gauge, effective number of gauge parameters, I get 16 minus 10 plus 16 bar, plus 16 minus 45 minus, and it oscillates wildly, but I can regulate it. I happen to recognize this because this is exactly the ghost level, ghosts of a constraint that forces a spinner to be pure. See the connection. Pure spinner is minimal orbit. This is how we recognize things from the beginning. It's the same type of things that occur in papers by Nathan Berkowitz and Nekrasov on partition functions for pure spinners, etc. But this is for minimal orbits in general. So this oscillates wildly. I mean, it looks terrible, but since it's alternating, you can regulate it, and it's well defined in analytic continuation. You look skeptical. It's fine. Yeah. No, but these are fine. You get the right numbers. Yeah. But you, yeah. That's one half plus 1/2 or minus. That's tricky. Yeah, these are okay. Trust me. So what is this? This is something that ghosts for ghosts, blah, blah, blah. So this number is ghost number. This will be the beginning of an L-infinity algebra, and D would be what I would call the one bracket of the L-infinity algebra. I realize that the level here may not agree with what everyone used before, or maybe it does in some version, but this is ghost number. Here is the 2 bracket. Yeah. So what's wrong with that? Well, all of these are I don't know. I think it's a, maybe we talk about that later. I think it's fine. So what you would like to do is to say that we introduce ghosts. Let me just talk about the gauge structure, not include physical fields for the moment. So this is a generic ghost, sum of all ghosts at different levels, fermionic, bosonic, blah, blah. So how do we know, how do we keep control of this? Well, we realized, due to the fact that we recognize this pure spinor thing from this example, that in general this has to do with minimal orbits. And actually, there is a it turns out that these are the positive levels of a certain superalgebra. That algebra we may call B of G. So if this is the Dynkin diagram of G, and for simplicity, let lambda be fundamental weight. It can be generalized. We add a gray node, a fermionic null node, in the place where lambda sits. So out from this, for example. It could be multiple lines if it's not a fundamental weight, but let's keep it sensible. And in fact, we managed to show that there is a denominator formula for this, which is, roughly speaking, the partition function for an object in the minimal orbit. So that was quite powerful, and that we can get sort of compact expressions for generators at any level. So we have sort of complete control of this algebra. This algebra is an algebra that underlies the L-infinity algebra. Sorry? The superalgebra. Well, the element, the ghosts are element in the superalgebra. And then I need, of course, I need explicit expressions for what the brackets are. And then there are 2 infinities to deal with. There is the infinity here, the number ghosts. And there is also the infinity, the fact that I have an infinite number of brackets. So why? I don't know what the L-infinity algebra is unless I can use something to build it. I need to write it down. What are the brackets? Exactly. Exactly. And if I don't know what these are, I don't know what to write. So I declare that they are in the positive levels of a superalgebra. And then they belong to it, yes. The structure constants of this superalgebra will define my L-infinity brackets. And then I can check the identities. However, this was sort of a simplification, because I immediately run into a problem. Let me do this picture again. R1, R2, R3, blah, blah, blah. And here is level 0. Here I actually would have in that algebra G plus R and negative levels. The first problem arises when I want to write down the two brackets, this one, as through the structure constants of this algebra. Turns out it doesn't quite work. So then you could either give up or you can do something better. It turns out what you need is, I can't do that here, I can do that here. What I need is that. So that is a simple observation that if I use the structure constants of this algebra, this would be, I call this GR plus 1, just because its rank is 1 larger. So this is also a superalgebra of this type, but with a bigger bosonic algebra. You can see this easily already in for ordinary gravity, that the structure constants, for example, I could imagine something like, let me not write down the concrete formulas. This whole thing turns out, superalgebras in general don't have unique Denkin diagrams because there are funny redefinitions you can do by sort of while reflecting in the odd roots. So these two are actually the same algebra. Yes? My lambda should be a dominant integral weight. Yeah. This depends on lambda because there could be multiple connections in here, but I assumed for simplicity that lambda is fundamental. Of course, the notation is not good. I should maybe say BG, comma, lambda or something. But in terms of this bigger algebra, there are very simple expressions that reproduce this for you. So since I have double extension, I can sort of do double grading here. And it turns out that I choose the grading, so I have this GR plus 1 at this line, and I have this B of G on this line. So I just try this horizontal line first. What I actually need to do is I need to, these representations always come in pairs. You could see that because there are some singlet fermionic elements here. I need to lift that up here and commute with something down here, etc., blah, 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 to get the rotation term. I don't do that in detail. This was discovered a couple of years ago by Jacob for the exceptional algebras. Then we did it in general. Yes. So that's a good sign, and then we can use, I mean, of course, always the fact that this is a least superalgebra, Jacobi identities, etc., and derivatives in some places, and we just check the Jacobi identity for this one. And we see, of course, as you all know, that it fails. It gives something which necessitates this. It gives the derivative of something here. So it goes hand in hand with reducibility. But at some point, actually, in this case, precisely at more or less around here, also this picture breaks down. This was what we thought was the whole story 5 years ago, was not the whole story. You get, here you got an extra term already in the 2 bracket for many cases. For all of these, I'd see more or less all of them except double field theory and ordinary geometry, of course. You get funny extra terms, but not in the 2 bracket, not in the identity for the, well, you get it in the identity for some higher bracket. At some point, you need something which we call ancillary ghosts. And lo and behold, they also fit into this one. So that's a second sign that, because they come in pairs, and at some point, we would activate something here. But they are also constrained, in a sense, with derivatives related to the section constraint. I don't go into details about that, I think. So the picture will be something like this: C1, C2, blah, blah, blah. And then at some point, actually, if you split this into forms, GL, using a section condition, always, in the section you always have a natural action of a general linear group. And then you can split these. Here you have forms plus the vector, of course. Here you just have forms, you just have form, but here something funny starts. You don't only have forms anymore. You also have mixed fields. And that means that this derivative, although it's nilpotent and nice, it will not be covariant. There will be some problem. It will not, how does it behave when you take it past transformation? It's not covariant, something extra is generated. That's roughly speaking what happens. Then we activate these. So let me call that K. So it looks like this. So there is, and these are constrained, they contain a derivative in some sense, and there is a sort of part of this is how the 1 bracket acts. And this going down is just simply, what do you call it? Inclusion? I mean, it's the same representation, you just lower it down, which means commutation with a singlet element here, actually. So this is the ghost structure. So we need to incorporate these fields in the gauss structure. And I will not tell you the details. What I will tell you to make my claims believable is that we have explicit expressions for all the brackets in the L-infinity algebra. So the n bracket with c's in, it's nice to write this way because it keeps track of the graded symmetric property of the bracket. For example, would look like this, and add means adjoint action in the superalgebra, of course. This is superalgebra commutator or anti-commutator, depending on which component, and then LC. LC actually only acts with a Gauss number 1 component, of course, which is the one generating gauge transformations. And plus terms that give contributions in the ancillary ghosts up here. And then, of course, I need also the brackets with ancillary ghosts, never more than 1, so it's not that bad. And these Kn are explicit numbers. They are Bernoulli numbers. And then you can check by forming some generating function of sums of these, that's using the generating function for the Bernoulli, the function that has Bernoulli numbers as coefficients, that all the identities of the L-infinity algebra are satisfied. It's a long calculation, but it works. So I think, Christian, to answer your question again, in maybe the same answer, if we couldn't keep, there's an n minus 2. If we couldn't use the superalgebra commutators in order to form the brackets, we would have been lost, I think. Yeah. Let me then, you wanted to ask something? Yeah? How does it look explicitly? Yeah. Yeah. It's actually, I mean, it's just, there are two terms, the transport term and the other one. They're both a single commutator of stuff. Of something here and something here, roughly speaking. I don't write it down. You can check in the paper. However, it now turns out that the signal for, say, this one to appear, to sort of kick in as an ancillary ghost, is the observation that at the next level, something new comes in here at height 1, so to say. And actually, call it R tilde. when something is there, you have the possibility of forming something here with one derivative, and that's when things start to happen. This can happen sooner or later. For E7, it turns out that you have something already here. For E8, where you have ancillary transformations already in the commutator of two generalized derivatives, things go wrong, because this algebra never contains an R tilde 1. Then you would need a ghost here. That would be the ancillary ghost corresponding to the actual ancillary transformation that you get by commuting two of these. This algebra is too small. This R1 always sits by itself here, which is easy to see because this is just the bosonic extension. At level 1, it just has R1, just like the fermionic one, couples in the same way. So this is the bosonic Lie algebra. Never anything here. So, can't we treat these cases? In that paper we wrote in April, we skipped that. But we also had realized what the solution should be. So in order to deal with these ancillary ghosts with ghost number 1, that will sit here, we cannot use this one. What we need to use is what is called a tensor hierarchy algebra, which we may denote like this. I don't have much time, or no time at all, actually, to discuss in detail what a tensor hierarchy algebra is. It's a funny algebra that, it's a superalgebra. It looks like the Borchard's superalgebra at positive levels, but it's not symmetric under exchange of positive and negative levels. It's not a contragradient superalgebra, meaning it's not, you can't derive it with the usual Chevalier construction and relations from a Dynkin diagram. So you need another set of relations. So we have what we think is a good definition, where we have more generators at negative level. These were originally introduced as a way of, for one thing, expressing the tensor hierarchies of the exceptional groups, because these are the representations occurring in the tensor hierarchies, but also at level -1, getting the embedding tensor. The embedding tensor is also the torsion of the extended geometry, which means that this looks like sort of promising, because if we get not only the ghosts here, but also sort of dynamical things, torsion, vielbein, torsion Bianchi identities, etc., it looks like an object that is better adapted to also doing dynamics, which I didn't have time to talk about. We are now at the stage, and by the way, they turn out to have this. Most importantly, they turn out to have something extra here precisely when we need it, which means precisely when these conditions are not satisfied. And that's a good sign. So this is work in progress. We're on the way to sort of patch up the calculation with the L-infinity algebra with this, at least for finite dimensional Lie groups. The tensor hierarchy algebra becomes increasingly complicated. So we know, roughly speaking, what it looks like for when we have an affine. And that would be, actually, since we're doubly extended, that would be the tensor hierarchy algebra, which is a super extension of, not of an affine, but of a hyperbolic algebra. So we know roughly what it looks like, at least the central parts that we need. But when we go infinite dimensional, it looks like we need to do case by case, because with the definition we have of these algebras, which we think is right, they behave in very interesting ways, which we think we should take that as our guideline, and this is what we use. So we hope that we will be able to do this for increasingly interesting cases like E10, etc. Yes, thank you.